Okay. Starting.
I actually want to make sure we get through 4.3, so I'll take questions after. So just hold on to your homeworks, get your notebooks ready, let's jump into it. There shouldn't be a lot, I don't think. Let's see how much extra explanation I have to give. We're doing 4.10, which is properties of matrix transformations. So yeah, by the way, last time we had technical difficulties, the camera wasn't recording. Of course, Evan was right behind the camera. The red light went off. Evan didn't notice because Evan never pays attention to anything, so blame him. So now, yeah, to answer his question, a part of what I'll be doing over my spring break is recording that lecture that should have been recorded if everyone was paying attention. But anyway. We're going to move on.
You know, it would be really convenient if you put the exam after the break. Then you can record the lecture.
Who wants that, honestly? Who wants
Raise your hand if you want it. Thank you.
See, he doesn't want it. You see?
Jhevon,
Only two.
there are students that legit didn't
The
know.
majority rules here. That's how it works. Okay, so recall matrices can represent linear transformations. Right, and remember we mentioned, well, I've kind of been mentioning it throughout the semester. The first lecture I really talked about it, but linear transformations, you kind of think of it as functions between vector spaces. You can actually get more general, think of it as functions between modules, but we're not going there. And so, linear, I'll define more what that means later on. So, A, which is m by n, can represent a linear function transformation which I would call t, which is a function from Rn mapping to Rn. Right? Okay. Oh, it's actually so I actually wrote this out once, where the number of columns actually tells you the dimension of the input space, which is your domain. The number of rows tells you the dimension of your output space, which is the codomain. T is just the name of the transformation. Sort of like f in f of x, name of the transformation. So basically, if we have a vector in our n, then T A of that vector will be in our n. Right? T A means the linear transformation. Represented by A. So, here is our space, F, N. We want to think more general, not R. Think in terms of that. And over here, we have Fm. So our x lives over here, and basically there's a function that maps that to someone over here, which we call TA. This guy is TA. The subscript A just emphasizes that it's represented by a matrix, M by N matrix. Right? Or this guy here is called the range of TA. So nothing here should be too crazy. It's sort of the same idea as functions, except now we're thinking of our domains and ranges as being multi-dimensional, which we might not have always thought of them as being before. So we're just generalizing functions. So this guy here is called your domain. This guy here is called the codomain. And the set of elements over here that you map to, you call those the range, that set. Okay. Then, as I mentioned before, matrix multiplication is really just composition of functions. Then we may think of something like T E composed with TA as the matrix. TA. And I'll talk more about what it means being represented by a matrix. If not in 4.10 later on. Because chapter 8 goes over sort of the same thing, and it goes deeper into it. But so, just want to get used to some of the notation first. Talk about it. If I know TA goes from Fn to Fn, I know TB goes from Fm to Fk. Then TB composed with TA is given right as TBA. Would be a function that starts where A begins and ends where B ends. So that would be Fn all the way to Fk. And so you can be over here. This is your Fn. TA gives you an output over here in Fm. Then TB takes that guy and puts it in another space called Fk. And what you can think of as a composition is doing is cutting out the middleman and going straight from this one right to that one. That would be your T, B, A. Right? A is applied first, B is applied second. It's composition notation, sort of like f of g of x, kind of. Okay. So far, nothing unfamiliar, I think, just new notation, really. We may also write Tx or Tx or T. Other notations that we can use to see that our function is given by a matrix, but we don't even specify the matrix. You can see any one of these if I'm talking about a general linear transformation. So let's first talk about what a linear transformation is. I think I also defined this before, but let's remind ourselves. Let L from a set A to B be a transformation. Then L is called a linear transformation. If two things happen. One, it preserves addition, both in the domain and the range. So it distributes across sums. And two, it preserves scalar multiplication. So you can factor scalars out. So if I have f of kx, then this is just k times L of x. So addition and scalar multiplication, it preserves the main two operations of a vector space. Right? Any function that does this, we call it a linear transformation. This you need to know this definition. Fy, we may also call them linear maps. They also be called linear maps. And L may be called a linear operator. Let's do a couple examples. Of course, linear transformations, we'd expect them to look linear, and that actually is the case most time, but not all linear things are linear transformations. So let's do some examples here. If I look at f of x, if I look at f, I define function as f going from, say, R to R. Right? These are two vector spaces. Given by f of x equals x squared, this is not linear. Since if I take f of x plus y, this will give me x plus y squared, which is x squared plus 2xy plus y squared, which is not the same as x squared plus y squared, which would be f of x plus f of y. Right? So the addition in the domain does not equate to addition in the range, so it's not a linear transformation, because point 1 fails. Point 2 also fails, because if I throw a scalar in here, then I'd get the square of the scalar, not the original. Another example. Again, going from the real numbers to the real numbers, if I define f of x to be the function 2x, this is a linear transformation. Because if I take f of x plus y, this is v2 times x plus y, this is v2x plus 2y, which is f of x plus f of y. Right? So point 1 holds. Also, if I take f of kx, I'll get k 2 times kx, but I can factor out that k, is k times f of x. So that holds. That's a linear transformation. Not all linear things in the conventional sense are linear transformations. So for example, f from R to R, if I define that to be x plus 1, which is a linear function, but it's not a linear transformation, it's not a linear transformation. Why? Since if I take f of x plus y, this would be x plus y plus 1, which is not the same as x plus 1, y plus 1. Right? I don't have enough 1s. So this would be f of x plus f of y. So it's not linear. So not every linear function is a linear transformation. It's very important that you realize that. And not surprisingly, we told you what all the subspaces of a vector space are. For example, in Rn, it's only the guys that pass through the origin. You notice that this is a straight line, but it doesn't pass through the origin. It's not going to behave like a vector space or a linear transformation if you use that as a function. So that's why. That's a function that does not contain our zero vector. So technically, things that look linear are linear transformations only if they pass through the origin or the zero vector of whatever space you're looking at. Linear transformations are super useful. We need to know when they work. They preserve vector space operations, so we know we're not killing our vector space by defining them. And that's always good. Now let's get to the meat of the matter, some new stuff. So there are some nice properties that we know about functions that we'd like to talk about here. Right? So for example, like on the very first quiz when I asked you about functions being one-to-one and onto and things like that, it turns out that those properties are actually really important properties. So how do we know if a linear transformation, if you give me a matrix, how do I know if, as a function that guy represents something that's one-to-one, something that's onto, or etc. So that's what we really want to get to here. That's what we're going to wrap up with in this section. Let's figure out how we're going to do that. Definition. We're basically going to use the same definitions as functions. So TA from Fn to Fn is called one-to-one or injective. If, what makes a function one-to-one or injective?
Everything from the domain maps to one single thing in the codomain.
Well, a unique thing in the codomain, right? So you could have a function that all map to one point, like a constant function. That would not be one-to-one. They have to map to unique elements in the codomain. if every x in Fn maps to a unique y in the domain. Equivalently, and this is the definition you'd use when you're proving something is one-to-one. T of x equals T of y implies that x equals y. Meaning if the outputs are the same, the inputs have to be the same. Because if the inputs were different, the outputs would be different. So you probably want to memorize that definition of one-to-one. It's defined by this implication. Remember, it's an if-then statement, right? So if this is true, then that must be true. And if this is false, then that must be false. So this is equivalent to me saying, if it's convenient for you to prove this, if x is not equal to y, then the transformation of x will not be equal to the transformation of y. It's pretty much the same. It's an equivalent statement. This is the statement, this is a contrapositive. Another definition, then we'll talk about how to actually identify when this actually happens. A TA be a transformation from Fn to Fm. The set, which we call the notation per TA, is the set of all x in Fn such that TA of x equals 0. The set of all elements that have a 0 output is a very important set. It's kind of like the null space of A or the kernel of T, which we actually mentioned before also. This book just goes around in circles. It's called the kernel TA. So a set of all guys in the domain that map to the 0 vector. Also, the set, the notation is R of TA, which is this is the set of all y in Fn such that T of x equals y for some x in Fn is called the range of the transformation. To put things in the language of 4.7 and 8, you can note the following. Kernel of TA is just the null space of A. And the range of TA is actually just the column space of A. So it's the set of all, it's the space that's spanned by the columns of A, that's where the input vectors go. I mentioned this last time, but I just want to make sure everyone actually remembers. When I say TA of x how you interpret that is actually A times X as a matrix, right? So we all remember that. Right, so that's what I mean by the matrix. This is a function represented by a matrix, meaning that this function is defined as multiply on the left by the matrix A. Right? That's how we define these transformations. And once you have a function defined that way in terms of a matrix, it will be linear. It will be able to distribute across sums, and you'll be able to factor out scalars. I just want to emphasize that, because what I'm going to do now is I'm going to prove a theorem, and you will need to understand that that's what's going on. I didn't write down the name of the theorem, but anyway, let's do it. Let A m by n be a matrix representing a transformation from Fn to Fn. Then the following are equivalent. Meaning they're all true or they're all false at the same time. 1. A is invertible. I actually want a square matrix. Make sure that's a square matrix. A is invertible. B. The kernel of your transformation will have only one element in it, and that's the 0 vector. 0 will be the only element that maps to 0 under this transformation. C. The range of the transformation will be the entire codomain. In other words, it will be onto, i.e., TA is onto. D. TA is 1-to-1. So it turns out if you have a transformation that's represented by a square matrix, then if your inverse exists, the kernel will only have one element in it. The range will actually be everything. It'll be onto, and at the same time, it'll be 1-to-1. You'll both get onto and 1-to-1. The inverse exists kind of tells you that because you think of this as the inverse function. And to do that, you have to be 1-to-1 and onto. So that's really nice, and we're actually going to prove this. So to prove the following are equivalent, we have to show that they imply each other. So we're going to prove that A implies B, B implies C, C implies D, and then D implies back to A. It all goes in a loop, and they'll all be true at the same time. So, assume A inverse exists, then what?
Rank of A is
It's easier than that. What do we want to show? We want to show that the kernel of this is 0. How do we define the kernel? It's a set of vectors that map to 0, right? So then, let's look at that equation. AX equals 0. What can you tell me about that equation if you know the inverse exists?
X is 0.
Right, it has only the trivial solution. This means that TA of 0 will give me 0, and no other x will map to 0. Which means the kernel only has a single element. the kernel only has a 0 vector. 0 will be the only element that maps to it, because this will have a unique solution given by the trivial solution. Because we know A inverse exists, and we have that huge theorem about what A inverse exists means. Okay? Let's talk about B implies C. What can you say about that? Now here you can talk about rank. It's probably not the only way to talk about it. So if we know that the kernel is 0, then that means AX equals 0 has only x equals 0 as a solution. Sure, you can say something like, this means the reducer echelon form is IA, which means that the rank of A is n, which means the columns span Fn, right? Because the column space would be n-dimensional, and we're in an n-dimensional space, it'll span the whole thing. You could also say something like, assume B is in Fn, then because we know this has a unique solution, we also know that Ax equals B will also be consistent for any B. And so no matter what B we pick, we'll find a solution to it, therefore the range is everything. You could have made that argument as well. But I think your book made a similar argument here. What about C implies D? Your book didn't do this one. So pretend I know that the range is everything. How would I prove that it's 1-to-1?
Almost starting it the same way. AX equals 0, so we know we have just this trivial solution.
We're not talking about Ax equals 0. That would be assuming something here.
Now we're talking about AX equals B.
Right. So since for every B in Fn, Ax equals B is consistent, right. But by theorem, right? Again, another one of those theorems that says the following are equivalent. We know that if this is consistent for every B, what does that mean? It means you have a unique solution. And what does that mean? Well, each unique output came from a unique input. So the outputs are the same, the inputs would have to be the same because the solution to this is unique. And now what about D implies A. Well, if AX equals B has a unique solution, then again, by theorem, this is equivalent to A being invertible. So now, this puts these properties in grasp of chapter 1. Right? Once I know my matrix is square, I will know all these things based on whether I know the determinant is non-zero or the inverse exists. It'll automatically mean I have 1 to 1, I have onto. This ends the proof right here. So in 4.9, you actually did transformations. The reason why transformation is used is you can think of these as distorting images in the plane in a certain way. One thing we know that is, for example, projections are not one-to-one transformations. They are linear transformations, but they're not one-to-one transformations because you can have different inputs becoming the same output, right? So let's say I have projecting down to the x-axis, right? Is it a unique vector that will become I? Let's say I'm in R2, right? And this is my I vector. Is that a unique output? Well, no. Any vector here would be boom, projected down on top of I. If I have a vector like this, boom, projected down on top of I. Anything down here will be projected up to I, right? So it's not a unique output, right? So it's not a one-to-one transformation, right? And you can know because the matrix will have a zero determinant, right? That's what are projecting on the y would look like. You kill the y value. This is the standard matrix of standard matrix to project on x-axis. Basically turn the y value equals 0. And again, we can see that because if I take 1, 0, 0, 0 and multiply it by the vector xy, the result will be x, 0. Rotations are one-to-one. Because for a given angle, only one vector would map to a origin. So if I'm in a plane and I have this vector, for a given theta, there's literally only one vector that will rotate to give me that one, right? So if my theta is like 30 degrees or whatever, right? There's no other matrix that I can rotate by 30 degrees to get this guy. It'll have to be a unique one. And what that means is you're actually invertible. You can have an inverse function. You could go backwards, right? So if I know that the original function was rotate counterclockwise 30 degrees, I could reverse that decision and rotate clockwise 80 by 30 degrees, and I'll get back the original input. The thing is, once you kill someone and he becomes I, you have no idea which one he came from. You can't reverse the function. you can't go back from your range back to the domain. You don't know who it came from. So, so let's say I performed a transformation here called TA, and that standard matrix will have sines and cosines in it. Then in this case we can write that the inverse of this transformation is just the transformation given by A inverse itself. And again, I can leave off the A if I don't. I don't want to really emphasize or name anybody. Or we can write T inverse equals T inverse. The emphasis is not needed. And you can add more to the theorem that I gave you guys last time, 4.8.8. The in-class version, because I kind of changed it from the other one. This gives us another huge theorem, 4.10.2. A n by n is a matrix, which you can say representing TA from Fn to Fn. Then the following are equivalent. So A all the way down to, I believe I gave you guys to N. This is from theorem 4.88.
Okay.
Okay. Okay, then we can add to that L. The kernel of TA is only the zero vector. M, the range of TA is Fn. Oh, TA is 1 to 1. Right, so this was all the stuff about A inverse exists, determinative is non-zero, AX equals 0 has only the trivial solution, A equals equal B has a unique solution, blah, 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 all that stuff that we've been building on for the whole time. We can add these to the list now.
Wait. M, N, O. You skipped N.
L, M, N. It's not an English class, come on.
Well, I wasn't sure if there was a next one.
Maybe you forgot some. Here's a nice proof to wrap up. Theorem. I thought it'd be nice because it uses the properties of linear transformations that we're going to talk about, that we have spoken about and we will talk about. And it's using stuff that we've already mentioned here. Like, so if kernel of TA equals 0, turns out if and only if TA is 1 to 1. I'll just prove both directions here. So assume the kernel of P8 is just 0, the set containing the 0 vector. Of course, here I'm assuming A is an n by n matrix. Then, if Tx equals Ty, what do we want to prove? That x must be equal to y, right? Any idea how we can do that? Well, a nice trick is the following. Subtract it from both sides. But t is linear, right? So what does that mean? It distributes across sums. So now here I have a new vector x minus y whose output is 0. But what must x minus y be? It must be 0 because the kernel is the 0 vector. Only 0 will map to 0. That's our assumption. This means that x minus y must be equal to 0 since the kernel is only 0. Which means that x equals 1. So if I assume the outputs are the same, the inputs have to be the same, assuming that the kernel is 0. Is the 0. The set contains the 0 vector. And that's one direction. How about we go to the other one? Assume TA is 1 to 1. That has to be true for a linear transformation. This implies there is no other solution. So AX equals 0 will have x equals 0 as the unique solution. Which means the kernel of the transformation is just a set containing the 0 vector. thought that was a nice route to show you guys because it shows us like proving things by manipulating an equation. Yeah, that's kind of all I wanted to show you. By the way, this is sort of, could you prove that? Maybe something I could ask on the test.
That's next week, right?
Yeah. You mean the following week?
Spring break?
Oh, remember the 4.8, recall, when we get there, 8.4, try from 8.4, 1 to 21 odd, and 22. It's not in our syllabus, but you should try it. It'll help you with those star problems that I put in the review, which I'm not going to put a question like that on the test. I'll probably put that on the last test.
You should have told us that it's
Huh?
time for the last test.
The last test is the last class.
Yeah, 18.
Is the last class the 18th?
I think so. Let me make sure.
It's like I hope marking it on his wall. Yeah, that's sort of all I want to do. Any questions? What?
Exactly 1 month.
Yeah. Any questions on the homework? 4.7, 4.8.
Yeah, it's the 18th.
Um,
4.7?
4.8.
Anything from 4.7? Yeah, so that huge theorem I gave you at the end here, that 4.10.2, you know that, you know lots of stuff connecting like chapters 1 through 4. Questions on 4.7? That was too easy. 4.8.
Question 19.
19. What does it say?
Something about like the rank is this number. Explain why.
It says if A is a 3 by 5 then the number of
A is a 3 by 5.
yeah.
Then
Then the number of reading ones in the reduced row.
19.
Is this it?
Yeah, that's it.
That's it. And reduced row echelon form of A is at most blank.
then the number of pivots is at most blank. Did it say anything else?
And
Why?
And why? Okay, so what do you think?
No, it's 3.
Rows and 5 columns, and we have 5 variables, x1 to x5.
All right, it's like A, B, C, D, E, F, G, H, I, J, K, L, M, N, O.
Then the most pivots you could have is 3.
Most 3. You'd have to have 1 pivot per row.
Why?
There are only, why? Because there are only 3 rows. There are only 3 rows, and there's at most 1 pivot per row. Right, remember pivot is the first non-zero number. If you already have a first non-zero number, anyone else cannot be the first non-zero number. A row can only have 1 first non-zero number.
If we invert that on the exam by accident, do we get like half a point?
You mean like tell me 5 is the answer?
Yeah.
No.
What's so hard?
There are different parts to it. You want me to?
Okay, what's the other one?
If A is a 3 by 5, it's the same one. Then the number of parameters, sorry, in the general solution of A vector X
Yeah.
is at most 5.
Is at most.
Oh, well, I gave you the answer.
It's at most 2. I think.
It's set at most or at
At
least?
most. Yeah, oh, wait, it is.
Yeah, it should be almost 2. But then there are more 3 pivots, so then if they're
If it's zero matrix,
Yeah, I'm telling you it's 3 if it was a zero matrix.
I think it'd be at least 2, not at most 2.
You can't have a multiple.
Because you can have more, right? Like if you have one.
It can be all the last two zeros and the first one has the false
Have they all been zero?
Right? That's 4 parameters there.
Write the column.
Right? And I mean, if you didn't start with a 0 matrix, you couldn't get a 0 matrix. But if if you had a 3 by 5 with all zeros, then it would be more. Anything goes. Right?
so what?
If it's all zeros, can that happen? Can that happen? In a triple zero, the general solution.
Yeah, so it's at most 5. And that would only occur if A is 0. Right? If you require that A is non-zero, is not the 0 vector, then it's like at most 4. Because you have to have at least one pivot holding it down.
So we have to answer them for that question?
5 would be. Right. 5 includes the possibility of it being a 3 by 5 0 matrix.
So this is the reason because A is equal to the 0 vector?
Oh, the Y is because the number of parameters, it's really the dimension theorem. We know that the number of pivots plus number of parameters must be equal to the number of columns, right? So if I'm assuming I have 0 pivots, if A is the 0 matrix, then that must mean the number of parameters has to be 5. It's using the dimension theorem. Right? That's the guy that links your leading ones to your nullity, your rank to your nullity. Is that it?
If A is a 5 by 3 matrix,
The same two questions.
Yeah.
Change the, instead of 3 by 5, they just put 5 by 2 for the same two questions.
Okay. So number of pivots at most.
No, 3.
Still 3. Right? Because if you have like you have just 2 0 rows here, right? There'll be there's no space because each pivot must be to the right of the one above it, but you can't go over to the right anymore. So it means in the reducer echelon form, this is the best case scenario. You have 2 rows of zeros. You still have only 3 pivots because I don't have another column to throw another one. And again, so the number of parameters here, I can set it to be 3. If A is a 0 matrix, it's at most 3. If A is non-zero, it's at most 2. I guess I'll probably emphasize that if I'm doing it in a test or something.
Professor, the slide 29 is proves if K is different than 0, then A and AA have the same rank.
29.
Yes, if K is different
K is
than 0,
non-zero, then
A and KA have the same rank.
right. right, so this is, if you start with KA, then what you do here is do a type 2 operation to divide by K in each row. And then you'd end up with A. And then you continue to the reduced row echelon form of A. So it turns out if your K is non-zero, KA and A will have the same reduced row echelon form. This means that KA and A have the same rank. Just use a type 2 operation to turn this into that. Other questions? Pass up the homework. Enjoy your break. So you want the test on Wednesday or next week?
Next week.
Next week.
Please.
Yeah, we can take it on a straight break.
No.
Who does not want it on Wednesday? No, does not want it after spring break.
Raise your hand.
No, no, no,
Loud
no.
and proud.
That's only one.
I don't want to do it in amazing hell.
There were the two students that didn't know.
Let's see the.
Life is hard.
You come back on the second, right? And our last class is the 18th.
So the second one? I mean, sadly, it will be that Monday to be
Yeah,
fair.
so the next test would have been like the 9th.
You're into every freaking day. I'm just, you know,
So if you get, if I give you the second test when you come back, the third test will be 1 week later, and the next test will be 1.5 weeks later.
I'm down with that.
Alright, just give me.
Like the last two are really short. It's nothing. Like eigenvalues and eigenvectors is like 10-15 minutes to learn it. It's not.
Alright, so got a plan?
That's it. Don't test.
Set in stone?
No.
No. Alright,
Ask
that's
Derwin.
it.
Ask Derwin.
No, wait, what? Oh, it's up to me now?
No. No.
You're the only one who had a problem. So what do you say, Derwin?
Majority rules.
If you say yes,
So I decide the
so
beta.
we're gonna go down.
Yeah, Derwin. By the way, I can give you his home address and everything.